So again, I want to welcome everyone to tonight's webinar. This is Weather Models 202. I'm Joe Deli Carpini, the Science and Operations Officer, and I'll be going through this solo tonight with a short presentation, and then we'll take some questions at the end. So I want to acknowledge, first of all, Jeff Manikin. He works down at a place called the Environmental Modeling Center down in Maryland, which is part of NCEP, the National Centers for Environmental Prediction. And his group goes through and assesses the models. They run verification on the models. They do a lot of testing for new model upgrades. So he's deeply involved in a lot of the model development. And a lot of what you see here tonight is what he provided to our office for our winter weather training toward the end of last year before we got into winter. So I think you'll enjoy a lot of this. So we're going to talk about computing precipitation type first, and then how the models compute snowfall. A lot of you, I'm sure, see those snowfall maps online, and you got to use them with a bit of a grain of salt. So we'll talk a little bit about some of the pitfalls associated with that. And again, this really just applies to the United States models, not the European, not the UK Met or Canadian models, just the American models such as the GFS and NAM and others, which we'll talk about. So for Weather Models 101, if you were unable to view that, you can certainly go back and take a look at that. Gives you a basic overview of the weather models. But numerical weather prediction, it really just involves the use of mathematical models of the atmosphere kind of to predict the weather. So really what they're doing is, and this is kind of the scary slide, is just calculate a bunch of equations and solve them. So it can do billions of calculations per second, much more than humans can do. Some of the equations are here on the right that they solve. But they do all the math for us. So think about it like just a big calculator that can run all these equations. They also produce different types of output. You can see some graphical output here on the bottom. They output maps, some statistical information like high and low temperatures. But each of the models have different resolutions. Some work on a much higher resolution, like the we show for thunderstorms or snow bands. They have different initial conditions, so the observations going in are tweaked a little bit. And some of the different parameterizations, which we'll talk about tonight, make the output differ, and that's what we want to see. So we want to see a forecast from the GFS maybe different than the NAM, different than the Canadian, different from the European model. Because if they're all the same, what's the point of running all these different models? So when we talk about precipitation type and snowfall, these are also determined by various algorithms, or simply put, equations. So some definitions, you'll see some of these on the slides tonight, just some abbreviations, ZR being freezing rain, IP, you might see that's sleet, SN, snow, and RA, rain. When we talk about SLR, we're talking about snow to liquid ratio, so that's traditionally 10 to 1, so 10 inches of snow for every 1 inch of liquid. QPF is a quantitative precipitation forecast. Just think about that as a liquid precipitation forecast, and P-type obviously is precipitation type. And these are some of the models we're going to talk about tonight, the NCEP models from the NAM, the WRF, which is actually the core for the NAM now, the North American model. We have the GFS, which is Global Forecast System, the RAP, Rapid Refresh, the HREF, High Resolution Rapid Refresh. And then we have our ensemble systems, the Short Range Ensemble, we call the HREF, the High Resolution Ensemble, the HREF, and the GEFS, or GEFS, which is the Global Ensemble Forecast System. Think of that, that's the GFS ensemble. So just a quick review, and this gets into model precipitation type. When we talk about the atmosphere, we take a look at what's called a sounding. So this blue curve is temperature, and it goes up with height. So if it's all below freezing, which is to the left of this black line, it all falls as snow. It's not going to melt, so there's no melting involved. Everything's below freezing. It falls as snow. When we bring in a little bit of warm air aloft, so kind of in the middle, maybe a few thousand feet up, where it goes above freezing, that's when we get sleet. So if you follow the line, it's below freezing. Then there's a little bit of partial melting here, and then it refreezes again into ice pellets. So that's when we get sleet. You've got just kind of a shallow warm layer aloft. And then freezing rain is caused by a deeper warm layer aloft. So this is a little bit thicker, and you can see as I switch back, notice how much deeper the warm layer is, and it's usually a little bit warmer too. So the raindrops completely melt. They don't have time to refreeze, but the ground is below freezing, so it forms ice as it goes in contact with the ground, and that's freezing rain. And obviously, if it's all above freezing, then we're looking at plain rain. So the original algorithm, and this goes back into the early 2000s, wasn't very good. It had some some strengths, but also some really significant issues. And for this sounding here, you can see here's the freezing line, this black line that I'm highlighting. Everything is below freezing, so this would be snow. But in reality, the algorithm was calling it freezing rain. It was intentional because the key was to have a high detection rate for freezing rain and sleet, which are the most hazardous types of winter weather. So even though the sounding looks like snow, this was going as freezing rain. So it really didn't cut it originally. So there are some other algorithms that are used today. One is called the Bourgeois algorithm, and this determines if there's energy to melt or freeze essentially the raindrops. Think about it like with thunderstorms. We talk about instability or energy. We talk about CAPE. It's similar to that. Is there enough energy to melt the snowflake or refreeze it? So that's one of the more commonly used. There's also one called the Baldwin algorithm. It's been around for a long time. Uses the wet bulb temperature. So think about layers that are above or below freezing, kind of like I just talked about through layers on a sounding. And then there's the Raymer algorithm. It looks in the vertical, so looking up, it looks at differences in pressure, temperature, humidity, and the wet bulb temperature, so a little more complicated. But those are just some of the other algorithms used today. Now today, the models use something called dominant precipitation type, and this is essentially a kind of a mini ensemble or group of different precipitation type outputs. So it uses the original NCEP, one that's called a revised NCEP, and then the Raymer and the Bourgeois, and they're based upon the wet bulb temperature primarily. So it obtains 5 answers and picks the dominant type out of the 5. So if there's a tie, it is based on the most dangerous weather. So freezing rain gets more weight than snow, which gets more weight than sleet, which gets more weight than rain. So again, it uses 5 different precipitation type algorithms, bunches them together, and then takes the dominant type out of all 5. So this ensemble approach is good because it captures the uncertainty with how these different schemes handle different temperature profiles and accounts for some error, but it doesn't account anyway for other uncertainties like the change of a low track, storm track, for example. So it really is just using these algorithms and nothing else. So today it's used for a lot of the models, the NAM, including the higher resolution, what are called nests. It's used for the GFS, the high-res WRF model, and all the ensemble systems, but it's not used for the RAP, the rapid refresh, or the high-resolution rapid refresh. Those use what's called an explicit algorithm, which I'll talk about next. It's not used for these other models because there's incompatibility with the microphysics. So those models only have 4 algorithms comprising the dominant precipitation type as opposed to 5. So talking about the RAP and the HREF, again, they don't use any precipitation type algorithm. It's solely based on the explicit prediction of the hydrometeor, so snow, rain, or even graupel, think about ice, reaching the surface from what's called the Thomson bulk microphysics, kind of a fancy term, but it's one of the microphysics packages. And you can get yes answers for multiple type. You can have it saying snow and rain and sleet at the same time, which is one of the weaknesses. And this is an example of that. So on the left is the NAM, where you've got the rain is green, snow is blue, you've got some freezing rain in the red, and you've got the sleet in purple. But notice on the RAP, it's got this area of pink, which is kind of a multitude of different precipitation types. So it's got everything going on at once, as opposed to one specific dominant type that's shown on the NAM nest. So for the ensemble systems, they all use the dominant precipitation type for all the members. And remember, for the HREF, there are 26 members, 31 for the GFS ensemble, and 10 for the HREF. So this allows them to compute the probability and a mean precipitation type. And again, it uses tiebreakers based on the most hazardous weather. So the freezing rain takes more weight than snow, which takes more weight than sleet, and more weight than rain. So again, these use the dominant precipitation type in the ensemble systems, and having multiple numbers allows us to compute probabilities and a general mean, and that's what we show quite a bit on our case studies. So here's an example just to show this from the SREF. This is the dominant precipitation type, showing rain to freezing rain to sleet and snow. And on the right, these will be the individual probabilities of rain and snow and freezing rain and sleet. So there's a number of ways you can look at this, as a mean on the left or individual probabilities on the right. So the thing to remember, these are called unconditional probabilities. They don't need to have precipitation necessarily falling. That will be a conditional probability. So they won't add up to 100 because no type is computed where precipitation is not falling at the valid time. So they're not going to automatically add up, but what you look at is kind of what's the dominant type. In this case, it's rain over Missouri, snow across northwest Kansas, and you've got kind of freezing rain and sleet in between those two areas. So that's how you kind of look at those. On the HREF, it's done in a similar way. You have different probability of precipitation types. So on the left, we're looking at snow. In the middle, we're looking at sleet. And on the right, we're looking at freezing rain. Rain is not shown here. But again, you get the general sense. Your highest probabilities of snow are here across New York, Pennsylvania, and inland areas. You've got a small area of sleet from D.C. up into New Jersey, and even a little area of freezing rain just to the east of that. So the danger with these is you cannot necessarily combine the probability for just precipitation and the probability for precipitation type. So think about it this way. If you have a 50% chance of precipitation greater than a ½ inch and a 50% probability of freezing rain, that doesn't mean you have a 50% chance of freezing rain greater than a ½ inch. You can't combine them, in other words. So, for the HREF, you could have 13 members with 1/100th of an inch of freezing rain and 13 members with ½ inch of rain. So what we do is you can compute a probability, but it's going to be a little bit misleading. So you really need to look at the individual members, what we call the postage stamps, to kind of determine what's the most dominant probability of precipitation type. Hope that's not too confusing. So now let's move on to the snowfall maps for the other part. And this is the thing I think most people are familiar with. So we're going to talk about all 4 of these bullet points here. So let's start with the first 2. So most of the NCEP models only have a snow water equivalent field and not an actual snow accumulation in inches. So what you're seeing on those snowfall maps is not snow accumulation, but kind of a snow water equivalent. And snow and sleet are tallied together, so there's no attempt to determine whether the snow can actually accumulate on the ground. So in cases where you have a lot of sleet, that's going to show up as snowfall, and the model is not simulating how much is going to accumulate on the ground. So that's a danger right there. So let's talk about these first 2 bullet points as we begin. And let's talk about snow to liquid ratio. So the snow water equivalent output, and that's what you see, it forces the user to apply his or her own SLR to obtain an actual number of inches of snow. Remember, the default is 10-to-1, which isn't always the case. In a heavy wet snow, it can be 5 or 6-to-1. In a light fluffy snow, it can be 15 or even 20-to-1. So you need to kind of take that into account when you're looking at these maps. They just assume a standard 10-to-1. And as it says here, many users apply just a generic 10-to-1 ratio, and that's not representative in many cases. So this will lead to an overprediction in events where you have marginal temperatures, think 33, 34 degrees, and an underprediction in events with very cold temperatures. Think, some of our blizzard in the end of January, we had snow water equivalents 15 to 20-to-1. So a lot of the model snow maps were well underdone. So that's an important thing to remember. So complicating things further, the snow water equivalent is tallied by combining snow and sleet. So in an event with sleet as the primary precipitation type, and again, that has a very low snow to liquid ratio, these 10-to-1 maps will show massive totals where they shouldn't. So think February 4th. We had mostly sleet across the area, a couple of inches of sleet. And the model is assuming sleet and snow accumulate the same way when they really don't. So this is a case from what was known as the Pi Day storm back in March of 2017. And you can see on the left, here's the 3-kilometer NAM forecast showing, the highest amounts here in eastern Pennsylvania, New Jersey, parts of the Catskills, and, even a foot of snow here in southern New England, when in reality, we had about 6 to 12 inches of snow here in New England, and the axis was farther west across central New York. So now complicating things even a little bit further, the snow water equivalent is computed by multiplying the precipitation by the percent of frozen precip, the snow ratio. So that means a storm that produces 1 inch of liquid in the model, say it's composed of 50% raindrops and 50% wet snowflakes, would have ½ an inch as the snow water equivalent. So this type of event probably wouldn't have accumulating snow if you're talking a mix of rain and wet snowflakes. but a 10-to-1 map would show 5 inches. So obviously that's well overdone. So again, it's multiplying the precipitation amount by the percent of frozen precip, the SLR. So in a case of mixed precipitation, it's going to really overinflate that snowfall total. And even an event with 1 inch of liquid in the model, say it had 80% rain and 20% sleet, it would make that 2/10 of snow water equivalent because of that sleet. So you'd have 2 inches of snow on a 10-to-1 map. In reality, you probably would have nothing at all. So again, it's overinflating these marginal situations. So what about snow depth? That's something that is a little bit better to use, and we'll explain why. So what's called the land surface model, so the interaction between the falling snow and the land, it does determine how well the snow can stick and how much can accumulate. Now, not all the models have accumulated snow depth, but a lot of the higher resolution ones do. So it uses an effective snow to liquid ratio based on the snow density. So it's computing the snow density. It's not going to use a straight 10-to-1. It accounts for the warm ground as well as compacting and melting. So it's giving you an instantaneous snow depth at that given time. So how can we use that? Well, this model evaluations group has been advocating to view the change in accumulated snow depth. So take the depth at the end of the storm, say it's at 36 hours, and subtract the depth at the initial hour as an alternative to the 10-to-1 map. So you'd be looking at the difference in snow depth from the current time out to 36 hours, which might be the end of the storm. That's a much more effective way, especially for early season events, maybe October, November, and late season events as we get into the later part of March and April, to really improve on those 10-to-1 snowfall maps. So it works somewhat well. As mentioned here, it can struggle a little bit with warmer ground, but we've seen it's actually done pretty well. It's also can be a little complicated to use. The value can actually decrease during the forecast period. So you want to take it right at the end of the snowfall and go right from the beginning. So you don't want to wait 48 hours if the snow is ending tomorrow morning, because it will start to melt and compact in the model. Here's an example of that difference. Again, it's the same storm here, the March 2017 storm. Again, note on the left here, this is a straight 10-to-1. It's showing the highest across Pennsylvania into southern New England. And this is the accumulated snow depth, which did a much, much better job. Notice here, you've got the higher snow totals, the Poconos into central New York and the Catskills, and lesser in the way of snow depth here in southern New England. It did a much better job. And this is, again, the comparison. Notice it lines up much better with the accumulated snow depth in the model. So here's another example. This was from 2010. This is an older example, but just showing, again, a difference in an event. This was in the, I believe, I'm trying to remember, this was, I believe, middle of the, I forget the exact date. It's not listed on there, but anyway, it shows the highest snowfall total. This was a mixed precipitation event, actually. So it's showing the highest totals across Oklahoma into Missouri, when in reality, it's only showing a couple of inches, 1 to 2, maybe 3 inches of accumulated snow depth. And in this case, here's actually what happened. There was virtually nothing, 1 to 3 inch snowfall. So again, this is a case where 10-to-1 was a bit misleading, and the accumulated snow depth performed much better. Oh, there it is, October of 2020. I'm sorry, I knew it was an early season event. So accumulated snow depth, it is available online for several models. And remember, it's only tallying positive changes. So most of the online sites do provide that now. The snow depth and the microphysics-based method it uses, they really cut these unrealistic 10-to-1 totals, but sometimes can cut them too much. So you need to use them with a little bit of caution. But there is some value, at least viewing them together, to determine where the model effectively doesn't support anything close to the 10-to-1 ratios. So you can see on here, here's the observed snowfall from this particular event, and you've got a maximum there in south central Pennsylvania. Accumulated snow depth did pretty well. I believe it was a little bit underdone. The 10-to-1 was much higher and overinflated, and the microphysics did pretty well too, based on the SLR. So that's using a variable SLR, in other words. So again, a case where these were good, but it cut them too much in this particular example. So most of the models, I'm sorry, let me move on to the next thing. The precipitation type and the snow water equivalent snow depth fields can be inconsistent. So this is an important thing. It can be showing one precipitation type, sleet, freezing rain, and the snow depth can be showing something completely different. So another weakness we have to talk about. So in this case, this was back in January of 2017. Note several inches of snow are being predicted here on the left. Even though the dominant precipitation type on the right is mostly sleet and freezing rain, and we're kind of focused here on central New York and Pennsylvania, although even here in southern New England, it's raining across much of the area in the model, but look, it's actually accumulating snowfall. So not exactly the best match. So what is used is something called the percent of frozen precip, and that's on the right. Notice it's in the 40 to 60% range across New York and New England. So if you apply that to the liquid precipitation of 1/4 to 1/2 an inch, that gives you about snow water equivalent of 1/10 to 1/3 roughly. So a rough 10-to-1 ratio becomes 1 to 3 inches of snow in about 3 hours, far less than the model snow map was showing here, which was showing in excess of 2 to 3 inches in that time. So the change in accumulated snow depth is also at least a huge improvement over the 10-to-1 map. In this case, the accumulations ended up being quite light, again, like a 1 to 3 inch amount. So just a case where you also need to look at the precipitation type and make sure that those things kind of match up as well. So the RAP and the HREF actually have an explicit snow accumulation field and was made a little bit more aggressive in its last upgrade. We're in this is called version 5, which is now. So a little confusing diagram here, but bottom line is it's showing is it has a better snow accumulation field due to an improved snow to liquid ratio algorithm. So that's the upshot. It's a little bit more accurate on these latest versions of the RAP and the HREF. And you can see on the right, the SLR can sometimes be a little bit too high. So a word of caution when using the RAP and the HREF output is the amounts can often be considered a potential upper bound, maybe a worst case scenario, as opposed to a more reasonable case scenario. So for the RAP and the HREF, use those with a bit of a grain of salt too. And finally, freezing rain is the most dangerous precipitation type, and most of the models, believe it or not, don't output a freezing rain accumulation. Well, why is that? Well, only the RAP and the HREF have an accumulated freezing rain and accumulated sleet. They were added in an upgrade back in 2018, something that's been asked for years from forecasters, but it's a very difficult thing to do. Now, there are some model sites, like shown here, that plot their own freezing rain accumulations, but what they're trying to do is combining the instantaneous precipitation type with a longer period precipitation, liquid, which leads to large overprediction. So think about it. If you've got freezing rain from 7 to 10 a.m. in the model and then rain, but you're using a rainfall 6-hour forecast going from 7 a.m. to 1 p.m., that's going to end up in overdoing the amount of icing over the area. So, from a qualitative sense, it's showing you where the maximum ice is located. That's good, but the actual amounts might be a little bit overdone. So here's some example of the HREF output. Again, this was this October case. This was an ice storm, for example, back in October of 2020. And you can see on the top, there's the 48-hour total precipitation. We've got an accumulated snow depth like we showed before, which is minimal. And the freezing rain actually didn't do too bad. A little bit, underdone on both models, but not bad. So in the future, all the models, the goal is to have them all have outputs of accumulations for snow, not liquid equivalent, but explicitly snow, freezing rain and sleet, and they are moving in that direction with model upgrades. So there are plans to generate precipitation type from information in the model microphysics, which isn't done now, and that will make the snow fields and the precipitation type information more consistent. So these recommendations will build upon existing modeling in the RAP and the HREF system, and that'll be exported into the future rapid refresh forecast system. So that's going to kind of be the future of the RAP and the HREF. Think more of like an HREF system. So the major effort here is going to be expand all of this capabilities into the global Ensemble system. Think the GFS. And probably don't have to say this, but it's a very complicated process to simulate in the forecast models. So, and just to finish here, what we're talking about in the future, again, on the left, this is called our rainbow diagram. These are all the models we have today on the left. So there's a lot of them. The goal on the right is to kind of group them by application. So we'll have things for example for short-range weather, for severe weather. We'll have things for hurricane season, things for medium-range weather in the next 10 days, and then seasonal forecasts and sub-seasonal, maybe 3 to 4 weeks and months at a time. So the models are eventually going to be grouped to tackle these things. The GFS will be the medium range, and the GEFS. This rapid refresh forecast system will be our short-range ensemble. So think about the HREF that we have today. That will be transitioned to this rapid refresh forecast system. So in other words, fewer models themselves, but more of these ensembles with individual members. And that's where these precipitation type efforts are kind of going into, the rapid refresh forecast system and the global ensemble forecast system. So that's a look at model precip type and snowfall. I hope it wasn't too confusing. It's a pretty technical topic. So what I'm going to do is we'll pause here, and I'm going to go through and see if we have any questions to answer, and feel free to throw some in the chat. Again, we're recording this, so you can always go back and watch this later on YouTube. Let's see, from Kevin, how old is the NAM model, North American model? Is NAM Nest a new approach to the original NAM? Well, the NAM is from about the 2010s. It originally was known as the ADA model back in the day, and we'll talk about that when we talk about the April Fool's blizzard. It's the North American mesoscale model, and the NAM Nest is a higher resolution of that. So if you go back to Models 101, we talk a little bit about that model, but that's known as more of a regional model. Its skill is showing things like thunderstorms, snow bands, sea breezes, snow squalls, that sort of thing. So comment from Joe that Ryan Mowry over at Weather Models has done some changes to make the snowfall maps better. Yes, that's correct. So a lot of the online models are doing, like we said, their own thing. So you definitely want to check some of those out too. But that's taking model output and kind of what we call post-processing. So the goal here with NCEP and with Jeff's group is to really do the work under the hood and get that output even better when it comes out. Let's see. So Sebastian says, heard that certain cams are not generally the best to use in forecasting winter weather, such as snowfall totals. Are true to this? Yeah, a lot of times the cams can overdo it. If you look at, say, summertime thunderstorms, a lot of times you'll see like these excessive rainfall amounts coming out of the model, and the same thing can happen in the winter time too with snowfall. So a lot of times you'll see these as more extreme solutions, and we talked a little bit about that in the HREF. You might want to use that more as an upper bound, or kind of a reasonably high total if things come together right. But yeah, on average, they tend to overdo things quite a bit. So there is some truth to that, Sebastian. And John just wants to know, what does CAM stand for? CAM is a convection allowing model. So it's a model that doesn't have an explicit algorithm for forecasting thunderstorms. And in fact, our next version of this model series, we'll probably do in the later spring or summer, we'll talk about model thunderstorm forecasts. So these are things that just allow convection or thunderstorms to develop on their own. There's no what's called parameterization, and they're actually very skillful. It's kind of the future of modeling. So it's a convective allowing model when we talk about CAMs. Let's see. Comment here from Ashish. Climate extreme events are increasing and intensifying. Moved to Boston last winter, didn't see these much intense and frequent snowfalls as I'm seeing this year. Yeah, so in the Northeast, actually, we've seen the greatest increase in precipitation events greater than ½ an inch, and most of that in the past 20 to 30 years. And we're certainly in a bit of an active winter period, especially the 2000s and 2010s have been quite active. So we're seeing a lot of extremes. We'll see a lot of these 12-inch snowstorms more often than we've seen before. So that's definitely a good point. So he also says, also some other countries are showing such patterns. How can we depict this from a climate modeling standpoint? Well, that's a little bit outside of what I've shown here today. Climate modeling is much longer term, think decades, in fact. So a lot of the climate modeling is looking at trends from now through about 2050 or even 2100. So it's done a little bit differently. It's done essentially using the GEFS and the GFS Ensemble to some degree, but and the climate forecast system is what's used for that. So it's a little bit outside of the realm that we deal with here in the forecast office, where we're talking about kind of the next 7 days, but certainly something that's being done in climate modeling with the climate forecast system. And Sebastian, that's just another comment for CAM thunderstorm total rainfall outlook. You don't necessarily want to look at the exact placement of the thunderstorm tracks. That's correct. You want to get a look at how much the model is predicting the rainfall. That's exactly right. So the placement isn't going to be correct, but somewhere it's probably going to get close to that rainfall as a maximum amount. So it's kind of the same thing we look at here when we talk about snow bands or even some of these thunderstorms. So, really the whole point of tonight's presentation was just to tell you that there are a lot of, assumptions made when it comes to precipitation type and especially model snowfall. It's not an exact science by any means, but it's something that's going to be improved in the next 3 to 5 years. I'm pretty confident of that. So just, we wanted to highlight some of these cautions because, again, it's 10 to 1. It's taking snow and sleet, which isn't always the best option. And even in mixed precipitation, where you've got a split of rain and snow, it's going to overdo the snowfall forecast. So, like I said, qualitatively, it's probably going to show you the axis of heavy snowfall pretty well. So that's pretty good. It's just the amounts are going to be usually a little bit suspect. Unless it for some reason ends up being 10 to 1, then it might do very well. So that's where you as the forecaster come in and you look at things like we've gone through on our case studies, the snow growth, how is that looking? Are we in that maximum dendrite zone, that minus 12 to 18 Celsius? Is that where your maximum lift is occurring? You're looking at the temperature profiles, like in the soundings. Is it all below freezing? Is there moisture all the way down? Or is there a little bit above freezing layer coming in? Different things like that. So again, nothing wrong looking at these snowfall maps and the model output, but just realize they are far from perfect. And again, as forecasters, we want to instill upon you, especially our upcoming students here, just using that knowledge to improve what the model is showing. So we have one more question here from Bob. Where does the data come from to initialize these models? Comes from a lot of sources, and you can check out Weather Models 101 on YouTube for a full description. But in short, it comes from all observational data. So think about weather observations from the airport stations, think about the upper air balloons, think about radar, think about satellite. A lot of the data comes from satellite. A lot of data comes from aircraft too. The ones crossing the oceans, the Atlantic, the Pacific, they provide weather data as well. So there's a lot of data coming in to initialize the models that we use. All right, so